Okay, welcome back, and this is going to be part 2 of the introduction to probability. So again, we're still dealing with the basics, terminology and things, but today I'm going to introduce some of the rules of probability that we're going to use later. So these are just basic rules, and I'm going to use examples to understand. So remember, we talked about the two different definitions of probability, okay? So we understand that the probability of an event, so if we have an event A, we know that the probability of A is going to equal, the number of outcomes that give A divided by the total number of outcomes in the sample space S, okay? And then we talked about, this is the theoretical, and we talked about the empirical definition of probability. And so I want to do some examples of how we could calculate those probabilities, okay? And let me see if I have a couple examples. Well, actually, you know what? I did do some of those examples already. So just remember from the examples I did, and we're going to do more examples. Trust me, I'm going to do lots of examples here. But I want to introduce a couple other rules for calculating probabilities, okay, that are very helpful, okay, and that are going to come into play later on in this chapter, okay, or this under probability. So one of the rules that I want to talk about is the complement rule, okay, and the complement rule is used quite often to simplify our calculations. So sometimes you can calculate the probability of an event by using the definition, but to do so would be tedious, okay? And we'll do examples where it becomes obvious of what we should use, okay? And if we use the complement rule in those cases, it makes our lives much easier, okay? So that's why I want to make sure you guys understand what the complement rule is, how to use it effectively, okay? So the complement rule is this. So if I have an event A, okay, and I want to calculate the probability of the complement. And the way we denote the complement of an event is by using the apostrophe or this symbol here, or what we call prime. It's an apostrophe, but it's A prime is the way we call it, okay? A prime is the way we denote the complement of A, okay? The rule is that the complement of A is equal to 1 minus the probability of that event occurring, okay? And again, this may make no sense to you, and that's because I don't have a context for it yet, but let me show you an example, and it'll make complete sense out of what I'm writing down, okay? So that is the complement rule. So let's do an example. So let's say I have this set, okay? And let's say I have the set of these numbers. Let's say I'm rolling a die, right? A fair die. So here's my sample space, and I'm rolling a die, right? And I'm going to roll it one time. And so what's the possible outcomes for one roll of a die? Well, I could get 1, 2, 3, 4, 5, or 6, right? Okay, well, in my sample space, let's put it this way. So let's say I got 1, 2, 3, 4, 5, and 6. Okay? Now, what if I want to define an event? So let's define an event here. Let's define A as getting an even number. So I get an even number on the roll of a die. Okay, that's the event I'm interested in. So I want to know what's the probability of A. Okay? Well, let's use the definition of probability, right? How many different ways can I get an even number? Well, I'm talking about even numbers, right? So what values, what outcomes on a roll of a die will give me an even number? Well, I can get a 2, a 4, or a 6, right? So the probability of getting an even number is going to be 3 out of 6, or 1/2, right, which is 0.5, right? So that's how we could calculate the probability of A, right? Getting an even number, okay? What if I wanted to calculate the complement? So what is the complement of A in this case, right? So here's the definition of the complement. So write this down. The complement of an event is all of the outcomes that don't give me that event. Okay? Now I might be confusing you, but so let me say this again. So if I want the complement of A, the complement of A are all of the outcomes that don't give me A. Okay? So think of it this way. So if I want all the even numbers, right? So that would be, let me partition this. Right? So let me split the sample space into two pieces, right? So in this piece over here, I have A, right? So all of the outcomes on that part of the sample space, if any of those outcomes occur, A has occurred, right? And over here, if any of those outcomes occur, then A has not occurred. In other words, the complement of A has occurred. So over here, we would denote this as A prime or A complement. Okay? So I hope that makes sense. So in other words, whenever you're talking about complements, you're splitting the sample space into two pieces. They don't have to be equal pieces, but they're two different pieces. So A is on one side, not A, or A complement, or A prime is on the other side. That's it. Okay? So in this case here, if I wanted to get the complement of A, so if I wanted to find the probability of A prime, right? By the way, what is the complement of A? What is A? A is even, right? Getting an even number. What's the complement of getting an even number? Well, that's not getting an even number. In other words, getting an odd number, right? So I can calculate the probability of getting an odd number, the complement of A, by just using the formula 1 minus the probability of A. Well, we found out is 0.5, so it's going to be 1 minus 0.5, which is, again, 0.5, right? Okay? But, and here, if we look at it, we could do it directly. What's the probability of complement of A prime? Well, use the definition of probability. How many outcomes give me an odd number, right? That's the complement, right? Well, there's 3. So it'd be 3 out of what? 6. So again, we still get 0.5. So we can use the definition of probability to get the probability, or we can use the complement rule. There are going to be some cases where the complement rule will be much faster and easier to use. Okay? So keep that in mind. Okay? So that's the complement rule. The next rule or definition that I wanted to talk about is conditional probability. Okay? So conditional probability is probability based on given information. It's conditioned on new information or given information. It's conditional, right? It's conditioned or based or depends on the given information, right? So we're going to talk about conditional probability. So conditional probability, the definition of conditional probability is this. Okay? So given that A and B are two distinct events, two events that we're talking about, right? So conditional probability is denoted P of A and then this vertical bar and B. Okay, so what does this mean? The way we would read this is the probability of the event A given that event B has occurred. Okay? So the probability of A given B. Okay, that's typically what we say. We should say probability of A given B. Okay, that's the conditional probability statement. The definition of that is it's the probability of A and B divided by the probability of B. Okay? The probability of A given B is the probability that both A and B occur divided by just the probability of B. Okay? So the one thing about conditional probability that you want to understand is whenever you're dealing with conditional probability, look at what's happening in the sample space. Normally, remember here, remember with the probability of A, right, with no conditioning, it was what? It was the number of ways, right? Number of outcomes, number of ways of getting A divided by the total number of ways or outcomes of getting S, you know? Right? Well, what happens when you condition on an event that has occurred? Well, the sample space shrinks. Okay? So no longer are you looking at the samples, all the outcomes in A, now you're just looking at all of the outcomes in B, in this case. Okay? So in other words, anytime we're dealing with conditioning, it's going to shrink the sample space. Okay? So let me derive this, and you'll see exactly what I mean. Okay? So let's apply the definition of probability to the numerator and the denominator. Okay? So what do we get when we do that? So, well, what does the top mean? Well, that's going to be the number of outcomes that give both A and B, right? Divided by what? The total number of outcomes in S, right? So this is the definition of probability for the numerator. Okay? Now let's do the denominator. Well, what's the probability of B by definition? Well, it's going to be the number of outcomes that give B divided by the total number of outcomes in S. Okay? So now, what happens here? Well, look at this here. Okay? This number and this number will always be the same, which means, look, I'm dividing by the same number on the bottom, which means this number and this number will always cancel. And so what am I left with? Look at this. I end up with the number of outcomes that give both A and B divided by the number of outcomes in B that give me B. Exactly what I've been saying. Okay? In fact, as we go through these examples, you'll be able to figure out the probabilities, the conditional probabilities, without ever having to use this formula. But you can apply this formula and it'll always give you the correct answer. Okay? So let's use this in a couple examples, and so that you'll understand both complement rule. We'll use the complement rule, but also in conditional probability. Let's see here. Okay, here. Let's do this. Let's say, for our example, let's say we roll a die, a fair six-sided die, 1. Okay, so we roll. So that's our experiment. Roll 1 fair six-sided die. Okay, so what's our sample space? Well, our sample space is going to be 1, 2, 3, 4, 5, 6. Okay, and so what do we want? Let's define A. So let's define event A is the set of 2 and 3. Okay? And let's define B as the set of outcomes 2, 4, and 6. Okay? So let's calculate the probability of A given that B has occurred. Okay? So let's start with that. So let's think about this. Okay? So I'm given B, so I know that B has occurred. So what do I know? I know that B has occurred, which means I got a 2, 4, and a 6. So all I care about is B, right? So I ignore A for a moment. Okay? My new sample space is B. So how many outcomes do I have in B? I have 3, right? So how many possible outcomes do I have? I have 3. Now, out of the possible outcomes in B, how many of those outcomes will give me A? There's only one. The 2. If 2 occurs, then A has occurred. Well, how many outcomes is that out of B? 1. So the answer is 1/3. Okay? So now let's do it again and apply the definition. Let's apply the formula. Okay? So what I just did was I used this, right? This idea that, hey, if I just look at B, because I'm talking about the sample space of B, well, as soon as I know that B has occurred, then I know one of these 3 numbers has happened. So then all I care about is, well, out of those numbers, how many will give me A? And the answer is 1. So 1 out of 3. Okay? So now let's use the formula. Okay? Well, what does this mean? It means the probability of A and B, right? And divided by the probability of B. Okay? So now, what's the probability of getting A and B? Well, so what's the probability on one roll of a die? Okay? What's the probability of getting both A and B occurring? Well, how many outcomes in both A and B, or excuse me, how many outcomes, if they occur, will give me both A and B? Well, which numbers are in common, right? Well, there's only one, the 2. Well, if the 2 occurs, then I know A and B has occurred. Does that make sense? So the top number is going to be 1, right? So now, let's do the bottom number. What's the probability of B occurring? Okay, well, oh, hold on a second. Let me go back. I misspoke. So it's 1, right? So how many outcomes give me? 1, right? So 1. 1 out of how many possible outcomes? That's what I forgot to say. I was getting ahead of myself. So let's start over. So the probability of A and B is how many outcomes give me both A and B? That's 1, right? The 2. Out of how many possible outcomes do I have on one roll of a die? That's 6, right? There's 6 possible outcomes. Divided by how many outcomes will give me B? Well, if I get a 2, 4, or 6, that's 3, right? Well, 3, probability of B is 3 out of how many? 6, right? Well, what happens? Okay, well, this is the same as 1/6 times, when you divide fractions, you multiply by the reciprocal, so it'd be 6/3, and what happens when you multiply across the top and the bottom? Well, this 6 will cancel with this 6, and I end up getting the same answer, 1/3, okay? So again, you can get the same answer both ways, okay? The formula will work, or if you just understand that I'm just going to divide the total number of outcomes that give me both divided by the total number of outcomes that give me the given information in the given sample space, B in this case, okay? So both, the formula will work either way, okay? Okay, so let's do this. Okay. Let's do an example, and to put it all together now, okay? Now I want to bring it all together, and I'm going to do a couple of examples. Yes, I'm going to do a couple of examples. I think that would be awesome. So I'm going to do one involving numbers, and then I'm going to do one involving a table. Okay. Okay, so let's do this. So in this experiment, I'm going to just talk about, so in this experiment, the sample size S, the sample space S, is the first 20 whole numbers. That means the number 0, all of the integers from 0 to 20, okay? So example 1, we're going to have S is all of the whole numbers, 0, 1, 2, all the way up to 20. Okay, that's the sample space. And we're going to define A as the even numbers. So the event of drawing an even number. Or you know what? Let's just do this. Instead of using A and B, let's start to change things up. Let's just define it as E, capital E. Let's do that, okay? And now let me define O as the event of selecting an odd number. So in other words, this is going to be the set of numbers from 0 to 4 all the way to 20. And this is going to be the set of all the numbers, including 1, 3, 5, all the way to 19. Okay? Now, let's answer some questions. Well, what's the probability of A? So let's first talk about the probability of A. What's the probability of A? Okay, we're just going to apply the theoretical definition of probability. How many outcomes out of the sample space give me A, or excuse me, not A, E. Sorry about that, E. Well, how many numbers are in the set that represent E? Okay, well, that's all the even numbers. Well, 0, right? 2, 4, 6, all the way up to 20. Well, how many? Well, we know there's going to be, out of 20, there's going to be 10 of them, right? 0, 2, 4, 6, 8, or 0, 2, 4, 6, 8, 10. And then, oh, no, it won't be. It will be, okay, so let's do that again. So we have 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there's actually 11. So I was wrong. So 11. So to find the probability of E, how many numbers out of the sample space give me an even number? 11. And how many numbers are in there? 21, because you have to include 0, right? So there's 21 numbers, so the probability is 11 over 21. And if we calculate that, we get 0.524. So 0.524, okay? So now, what about the probability of odd? Well, there's a couple ways we could do this, right? So the first way is just to use the definition of probability. Well, if there's 11 numbers that are even, right? And there's 21 numbers. How many numbers give you odd? Well, it's going to be what? 10. So 10 out of 21 is going to give us odd numbers. So the probability is going to be 0.476. Okay? But there's another way to get this. We can use the complement rule, right? Because remember, there's only a parity. For numbers, the parity of a number is even or odd, right? So there's only 2 of them. So I could get the same number by using the complement of E, right? So the probability of getting O is the same as the probability of the complement of E, which is just 1 minus the probability of E? Well, we know what the probability of E is. We just calculate it, 0.524. Well, what's 1 minus 0.524? Well, it's 0.476. Same thing. Okay? So there's an example of using either the complement rule or the definition of probability. Okay? Okay, so now let's go to the next one. And let's say B. Let's calculate the probability of A given, or E given O. What's the probability of getting an even number? Okay, in this case, let's see here. Let's see here. What? Okay, good. Okay. Let me see here. Oh, you know what? Let me redefine this. Okay, this is good so far. So let's stick with this. So this is a good example. Let me change the sets a little bit. Okay. So let's do this. Let me add another set. Okay. So let me add. So now we have EO. Let me do this. Let me add event C. Okay. So let's C equal the event that I have a number greater than 13. So this would be 14, 15, 16, all the way up to 20. Okay. So let's define an event C, and now let's use that to do conditional probability. Let's do this. Let's calculate for B. Let's calculate the probability of E given that C has occurred. Okay, let's figure out what that conditional probability is. So how do we do this? Well, let's just apply the definition. Okay. Well, actually, no. Before we do that, let's just think about it. Okay. If I know that C has occurred, then what does that tell me? It tells me that I know that I got a number that's bigger than what? 13. I know that I can only consider numbers bigger than 13, so 14 and higher, right? So given that I know that C has occurred, I know that I can only look at the even numbers. If I want the probability of getting an even number, I just need to know how many even numbers are bigger than 13. Well, there's 14, 16, 18, and 20. 4. So I can think about this as, well, I've got 4 even numbers that are in C. Out of how many numbers are in C? Well, 14, 15, 16, 17, 18, 19, 20. 7. So the probability is going to be 0.571. Okay? Does that make sense? I hope it does. But let's use the formula and prove it. So the formula says, take the probability of E and C, divided by the probability of C. Well, let's apply the definition of probability, right? So how many ways can I get E and C out of the total possible outcomes? Well, what's the total possible outcomes I can get if I select one number out of the sample space? I have 21 numbers, right? That's the sample space. Out of those 21 numbers, how many of those numbers will give me an even number and a number bigger than 13? 4, right? 14, 16, 18, and 20, right? So it's 4 out of 21 numbers. So on the top, that probability is 4 over 21. Now what about the bottom one? How many numbers are in C out of the sample space? Well, 7. 7 out of what? 7 out of 21. Well, remember, the 21s are going to cancel, and I get 4 sevens. Okay? I hope that helps. Okay? But yeah, either way, you can think about it by just using the idea that, hey, what's going on with the sample space, and then focusing on only the things that are given in the given sample space, right? In the conditioned sample space. So focus on whatever you're conditioned on. That's going to be your new sample space. And then you look at how many numbers out of that sample space, the new sample space, give you your event you're interested in, okay? And if you're confused by that, or if that doesn't work, just check it with the formula, okay? Okay, so now what about if we turn it around? Let's do C. C, we're going to turn it around. Let's go this. C, we want the probability of getting C given that E has occurred. So now, what's our sample space now? It's reducing to just the even numbers, right? So out of the even numbers, right? So how many even numbers do we have? 11, right? So now, instead of using 21, now our sample space is reduced to 11. Out of the 11 in our sample space, how many are bigger than 13? Well, we've got 14, right? So we're only talking about even numbers. So we got 14, 16, 18, and 20, right? Or no, I'm sorry. How many numbers are bigger than 13? Yeah, of the even numbers, how many are bigger than 13? So again, yeah. So we got those 4 numbers. So 4 out of 11. That's our answer. So in other words, it's going to be 0.364. Oh, yeah, 364. Okay. So, but again, let's use the formula just to show that it works. P, C, and E, again, it's C and E, that's going to be the same. C and E, right? That's the same as before, right? Divided by now the probability of E. So in this case, the numerator is going to stay the same as before, but the denominator is changing, right? So what's the probability of C and E? Well, that's going to be how many different outcomes giving both an even number and a number bigger than 13. Well, that's 4, right? Out of how many in our sample space? 21. Divided by the probability of E, which is how many numbers are even? That's 11. Out of 21. And again, the 21s cancel, and I end up with 4 11ths, which is the same thing. Okay. I hope that makes sense. Again, I like these examples. They're different examples than what I do in class. So again, this is a good practice to look into, and I hope this makes sense. Now, let's look at another example. Oh, let me go back. There's, oh, by the way, so here's the thing. So we just calculated 2 probabilities, right? This was 0.364. And then we also calculated the probability of E given C. And that was 4 out of 7, which is 0.571. Now, those two probabilities are not the same. And that's going to be important later. Okay? So remember this. The probability of C given E and the probability of E given C will usually always never be the same. Okay? But just notice that. Okay? Also, what was the probability of E? What was the probability of E? That turned out to be what? 11 over 21. Okay? And so notice that these probabilities are not the same either. Okay? That's going to come up later too. Okay? But again, just make sure you're able to calculate these probabilities. I think that's it that I want to go over. Let's see here. Okay, here's another example I want to do. Okay. This will be the last example. So let's say we have a table and we're rolling 2 dice. Now we're going to roll 2 dice and we're going to create this table, okay, of all of the possible outcomes. Okay, so this is going to give you a table, but again, this is an example of where a lot of things are going to come into place, right? So these are, if we take 2 dice, okay, so we have dice 1 or die 1 and die 2. Okay, well, we can get six that way, so we can get a 1, 2, 3, 4, 5, 6, and we can also get oh, I messed up. I hate that. Let me do that again, sorry. So one thing about doing whiteboards, okay, so let's say we do 1, 2, 3, 4, and 5. Okay, so we get 1, 2, 3, 4, 5, 6. Okay, so now I'm going to fill in the board real quickly. And because what I'm going to do is, what are all the possible outcomes I could get on the roll of 2 dice? Well, I could get a 1 and a 1, right? I can get a 1 on the first one, 1 on the second one. I get a 1 on the first one, a 2 on the second one, and so on and so forth. So let me fill in the table very quickly with that pattern. So I could get, and the first number will be the number on the first die, the second number will be the number on the second die, okay, just so we can be clear. So this will be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 2, 1, 2, 2, 2, 3. Okay, so that's the table, okay? So here's the setup. Let's say this is what we want to do. Here, these are the 36 possible outcomes for the roll of a two dice. Okay? So let's say we have this set up, and suppose we want to count the number of dots that are on the faces of the dice when they're rolled. So in other words, we want to sum up the dots and get the total number of dots. So in other words, sum the numbers that we get. Okay, what would the outcomes for the sums of the numbers be? Okay, let's write that down. So the sample space, so here's all the possible outcomes, but here's the way we're defining the sample space by the sum, right? So let's X equal the sum of the dots on the two dice. Okay? So the sample space is going to equal what? Well, what could the sums be? Well, if we sum these up, well, the first one, what's the minimum sum that I could have? Well, the minimum two numbers on two dice is 1, 1, right? So the minimum sum I could get is going to be 2. And then I could get a 1, 2, which would give me 3. Then I could get a 1, 3, which would give me 4, and so it goes on up there. Now, what's the largest sum that I could get? Well, I could get a 6 and a 6, which is 12. So what it turns out to be, the possible outcomes for X would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? So that's our sample space. Okay? Now, we're going to use this as our sample space, but we're going to use this table to calculate our probabilities. Okay? So, the questions are the outcomes in S equally likely? So remember, to be equally likely, the probabilities of all these outcomes have to be the same. If one of the probabilities is different, they're not equally likely. Okay? So let's take one and see if they're, or take two and see if they're different or the same. Now, I don't want to go through all of these. All we have to do is find two that are different and we're done. So what's the probability of getting a sum of 2, right? Well, how many of these outcomes gives me a sum of 2? Well, it's only one, right? It's the first one, 1 and 1, right? There's only one way to get a 1 and a 1. So this one. So this here, the probability of getting a 1, or excuse me, getting a 2, not a 1. Getting a sum of 2, right? The probability that X equals, right, the sum of the dice equals 2, right? Well, how many different ways can I get 2? Only if I get a 1 and a 1. Well, that's going to be 1 out of how many possible outcomes? 36. Okay, now, let's just do the next one. A 3. How many different ways can I get a sum of a 3? Well, I can get a 1 and a 2, a 1 on the first die and a 2 on the second die. That'll add up to 3, right? But what if I get a 2 on the first die and a 1 on the second die? Right here. How many ways can I get 3 then? Well, the probability of X equal to 3 is going to be 2 out of how many possible outcomes again? 36. Are those two the same? No. So are they equally likely? No. We're done. So the answer is they're not. These outcomes are not equally likely because the probability of getting a 2 and the probability of getting a 3 is different. Okay. Okay, so now let's look at the probability of getting a 4, right? Okay, so let's do that. What's the probability of getting a 4? Okay, so let's see here. Let's do this A. Let's make this A. That was about equally likely. So B, let's say the probability of X is equal to 4, right? The sum is equal to 4, right? So what's the probability of X being a 4? Well, I'm just going to use the definition of probability. How many outcomes in my table add up to 4? Well, this one adds up to 4. Well, if I go across this diagonal, I get them all. So, this number, this one, and this one. There are no other combinations that will give me 4 as a sum. So that means the probability is going to be 3 out of 36, right? Which reduces to what? 1 out of 18, which 1/18th, of course, we want to make sure we write these as decimals. But you don't have to, just for the sake of understanding. So it would be 0.056, right? Or you can leave it as a simplified fraction too, okay? Not a big deal, okay? A lot of times, it's like I do on exams and stuff, I always have my students write it as a decimal, but in reality, you could just leave it as a fraction. Just depends on what you're asked to do, okay? Okay, so now, what's the probability of a 6? Again, it's the same idea. How many outcomes give me a 6 as a sum, right? So where's the 6? Let's look at it. Well, right here, 1 and 5, right? And then I'm just going to go down the diagonal. Let me use blue. So look at it, 6. 1 and 5, right? So then if I go down the diagonal or across, it's going to be those 5, okay? So in other words, the probability of getting a sum of a 6 after one roll would be 5 out of 36. Okay? And now the next one says, let E, so we're going to define an event. So D says, let E be that the outcome for the sum is an even number. Okay? So the sum is even. Okay? And let G equal the event that the sum is greater than what? 9. Okay? So now what we want to do is, what is the probability of E? Well, what's the probability of E? Well, how many different ways can I get an even number? Okay? How many different ways can I get an even number? Well, that means I'm either going to get a 2, 4, 6, 8, 10, or 12, right? So I need to find what's the probability of getting a 2, a 4, a 6, 8, 10, and 12, and then add all those individual probabilities up, okay? So in order to get the probability of E, I have to take the probability of x equal to 2 plus the probability that x equals 3. So remember I'm using the condition, that one of those properties from the last video on probabilities, properties of probabilities. One of the properties is whatever the event that I'm interested in, it has to be equal to the sum of the individual outcomes. Well, I have to do these outcomes here, right? Well, I have to find the probabilities of each one of these outcomes, and then they all sum up to the event that I'm looking for, okay? So this is the probability of x equal to 4, okay? And then plus the probability that x is equal to 5, or excuse me, not 5, hold on a second, even numbers. Stay focused, Mark, hold on. These are even numbers, sorry about that. So 2, 4, 6, 8, and plus the probability that x equals 10, plus the probability that x equals 12. Okay, so now, let's count those up, okay? So again, remember, all you have to do is find one and go through the diagonal. So if I want even numbers, well, that's this one. That's an even number, right? This is an even number, and this is an even number, okay? So those will give me the even numbers. So 2, 4, 6, and then 8, and then 10, and then 12, okay? So if I count those, so I go, this is 2, this gives me 2, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I get 18 out of the 36. So I can just count all of the outcomes instead of doing this. I can just count all the outcomes that give me an even number and then divide by 36, right? So I don't even have to do all this if you think about it, right? Just remember, go back to this total, right? What are all the sums that give me even numbers? 2, 4, 6, 8. Well, if I just go back, well, I know this gives me an even number, this sum gives me an even number, these 3 give me an even number, these 5 give me an even number, and I just keep skipping, right? So, and I get 18. So the answer is 18 out of 36. Well, so it's going to be 18 out of 36, which is what? Oh, 1/2. Right? So that's easy, right? Again, just go back to the table, count all of the possible outcomes that give me what I'm looking for, an even number, and divide by the total sample size, which is 36 in this case. 18 divided by 36, which is 1/2. Okay? But I'm showing you this because remember that you can do it this way too. Okay? Well, we already figured out what's the probability of 4 and 6. Right? 1 out of 18, 5, or excuse me, 3 out of 36, 5 out of 36. If you keep going, so what's 2? Well, let's just fill it in. 1 out of 36, right? We did that one before too. 1 out of 36. This is going to be 3 out of 36. This one's going to be 5 out of 36. Okay? The next one is going to be, again, 5 out of 36. And then this one's going to be 3 out of 36. And the last one's going to be 1 out of 36. Notice something here that we're going to talk about later. Okay? Add these up. Right? You've got a common denominator, so all you have to do is just add up the numerators and divide by the denominator. So you got 1 plus 3 is 4, plus 5 is 9. 9 plus 5 is 14. Plus 3 is 17, plus 1 is 18. There's the 18 over 36. Notice also something else. Notice how as you go from 2 all the way to 12, the probabilities go up and then go down by the same amount. It's symmetric. Okay, but we'll talk about that when we get to distributions. Okay, so that's how we calculate that one. So a couple of different ways to attack that one. see here. Now, let's do the event G. Okay? The probability of G, let's do it again the same way. Well, how many different ways give me a sum greater than 9? Well, where's 9? Well, this is 8, right? This was 8. Well, look at all the ones at 9. Well, anything higher than 9 is going to be on this side of the table, right? Oh, greater than 9. Greater than 9. I don't want, hold on, sorry about that. Greater than 9. Okay, so I don't want to include 9. So that's 10 or higher. Okay? So which numbers give me 10 or higher? Well, that's going to be everything to the right of this staircase. Right? Or below. So how many numbers are in here? 1, 2, 3, 4, 5, 6. So 6 out of 36. Or 1/6. Okay? So we know, just by counting the numbers in the table, it's going to be 6 out of 36 or 1/6. But we can also apply the same probability, right? What's the probability of getting a 10, 11, and a 12? Well, we could add up those probabilities. The probability of getting a 10 is 3 out of 36. The probability of getting 11 is a 2 out of 36. And the probability of getting a 12 is 1 out of 36, and do the same thing. Okay? Either way, you'll get the same answer. Okay? So, let me see. I think that's it. I think we'll finish there. So that finishes up the basics of probability as far as this section goes. So this is part 2 of basic terminology and basic statistics and some of the basic rules, the complement rule and the definition of conditional probability. Next time we're going to get into the rules, the other rules like the addition rule and the multiplication rule, and we're going to introduce compound events in the idea of and or statements. Okay, so that'll be next time. And now what we're going to do is we're going to take everything that we've learned and apply it to other situations where it's going to look complicated. But again, if you just stick with what we've been doing, it'll just be piece by piece. You'll get the correct answer. Okay. Okay. Thanks, and I'll see you next time.